So if you are taking physics honors, chances are that you're kind of stuck a place where the concepts are getting a little tricky, and it's hard to kind of even explain what the heck is going on, right? Um, and that's particularly true for what I believe is kind of the hardest unit to in the beginning of the year. So free body diagrams. Um, Now, the biggest formula that you guys will definitely cover is the F equals ma formula, okay? And more specifically, this is the net force acting on some object is equal to the mass times some acceleration, okay? Now, today, I want to go over two specific problems that, two specific problems that are going to essentially be what I consider very difficult, but also some of the most conceptually cool stuff. It's the physics that'll really matter in the long run. So consider that you have some block. So this is a frictionless surface. Okay, you have some block here. This is a horrible drawing. Okay, so do that, do that, do that. There we go. Kind of a not straight, but it works. Actually, let me make this a little bit better. Okay, so there's some kind of block here, right? And me, I'm some person over here. I'm dragging this block this way, so I'll make myself look a lot bigger. So let's just say I look like this, and I am dragging this block this way, okay? To the right. Now, the way to actually understand what's going on here is to do what we call a free body diagram. And the first question I have simply for you, and think about this, is, well, draw the free body diagram. Tell me what forces are acting on this block. Now, the incorrect answer, now, of course, we would always start with mg. In physics, mg is the first thing that you should be looking for. So there's a force acting on this block, pushing it down. Okay? There's no friction. And if there was, all you would have to do is simply say there's friction going the opposite way. Okay? But in this case, there's no friction, so we don't have to worry about that. Now, the mistake here is thinking that, well, okay, well, it's just going to be the force going up here, the tension, right? If you didn't get that part wrong, well, you might think, okay, well, it's just going to be the opposite force, the normal force is what we call it, pulling it, preventing it from crushing the ground and going infinitely deep. And of course, from here, we want to know what kind of force is happening horizontally. Yeah, there's a diagonal force happening here, and let's say we knew that the tension force was like 50 newtons, okay? Let's say the tension force was 50 newtons. That's how much I'm pulling in general, diagonally. But the force acting horizontally, we can't use F equals ma with that tension equals 50N. We have to consider the horizontal force, which is just going to be, given by some theta, 50 cosine theta. Correct? Okay. So the force in the horizontal direction is 50 cosine theta, and that's what we can use to solve for some problems. However, there's another mistake here, and that mistake is thinking that the normal force is exactly equal to the mg. The normal force is smaller, and make sure when you draw your free body diagrams that it's pretty clear that these two are different sizes. Okay, because there's another force pulling it up, right? This guy right here, me, I'm not just pulling the block horizontally, I'm pulling it a little bit upwards, pulling it diagonally a little bit. And so there's another force here, okay? And this force right here, is 50 sine theta, okay? So it's the vertical opposite kind of vector. It's the y vector, you could think about it, okay? So all in all, this is your free body diagram. Now, let's say I asked you for the acceleration of the block. How do you find the acceleration, given that the block was 100 kilograms? Okay, so remember, all we have to do now is figure out, okay, we know the free body diagram. Now we just do F equals ma and find F net. So the net force acting on this block is, of course, we have the mg here, and of course, you can label mg as negative or Fn as negative, whatever you desire. But ultimately, I'm just going to say mg is positive, that this going down this way is positive and going this way is positive. So mg minus Fn plus 50 sine theta. Okay, this is really critical. Okay, so that's why when you find the net force, you can't just say it's mg minus Fn and say these two cancel out, because there's a net force acting a little bit from my pull. And of course, this would be in the y direction. Now, it's kind of useless, but F net in the x direction is actually useful to us. The only thing in the x direction, the horizontal direction here, is just the tension force. Right? It's tension. X direction, which is just equal to 50 cosine theta, right? There's no friction here, so we don't have to have a minus FFR and do all those things. And we just set that equal to ma, which is equal to 100 kilograms times the acceleration. And of course, acceleration in this case would just be 1/2 cosine of theta, and for whatever theta you're given. If it was, let's say theta was equal to like 45 degrees, well, this would just be root 2 over 4, okay? But none of that's really important. The important thing you have to get here is how we got the free body diagram. And another case that I want to look at here, this will be the last one of this video, is looking at an incline. Okay, so let's say you have some block, right, sliding down some incline. It's going down this way. Okay, so there's a sliding down like that. Okay. Now, the question is, well, what is the free body diagram for this? Now, luckily, if you want to start with mg in this case, you are correct. And I am going to give, let's say, an angle, some theta, right? So the first step is indeed correct. There is a force going that way, and I will just label it as mg. Just do this, mg. Okay. However, the block is on an incline. It's not on a flat surface, so the normal force isn't this way. This is not the normal force. The normal force is actually this way. Okay? And the normal force here is, because it's not tilted in the same way, we have to kind of reorient our understanding. Okay, so how do we find the net force, right? That's the key question here. And there's, once again, no friction involved in this problem. And the way to think about it is, we're given theta, and so we need to use some trigonometry. Now, to make this easier, I am going to extend this mg line all the way down here. And now, I want you to notice something, okay? So this is just mg here. So this angle, I'm going to draw right here, is 90 minus theta, correct? That's 90 minus theta degrees, right? Because there's a right angle formed here, and so this is 90 minus theta. Now, given this information, well, how do we get to Fn? Well, if we continue to draw a line, right, through this Fn from this point right here, what would happen is that you would notice, essentially, that the angle formed, because look what happens, right? This is actually going to be, there's an angle here of this angle. Well, this right here is also theta. Can you see that? Hopefully you can. And because there's a right angle formed right there. So the only way for these two angles to add up to 90 is if this one is, well, the remainder of that angle. So theta and theta are happening together, okay? And this is the tricky part here, seeing this. And what I would recommend is draw this line here. This line will really help you to see, right? Because we have a 90-degree angle here, and to finish by the the supplementary angles, right? This entire pair or trio of angles have to add up to 180. You have 90 degrees, so 90 degrees left. So the remaining angles theta. Okay, now we get it. We get it, right? So this line right here, right? Because remember, this thick blue line, right? This one right here is mg, which means this line is mg cosine theta. Okay? Because remember, I'll show you this. We can flip this like this. Hopefully that helps you see it, right? If that makes you see it any better, right? This is theta. This is theta right here. And this is the hypotenuse. This is the leg. And this is the adjacent. So it's mg cosine theta. Okay? So there you have it. Which means that the force up here is also just mg cosine theta. So that's a little tricky step right there. And hopefully you understand how you get this, okay? So the way that you explain and think about this is that you understand that, first of all, you can just memorize that it's mg cosine theta, but to actually draw it, what you need to do is utilize the fact that, okay, you have a free body diagram, you need to see the angles. You need to draw the triangles and figure it out that way. Because otherwise it's kind of a pain. And an even harder thing to realize is like there's a step here. Right, this is mg sine theta. And you see that this is a right triangle, right? Because we have this right triangle with mg cos theta and mg sine theta, which indeed does mean that the way that this force is falling in the x direction, this right here is, right, we do have an mg sine theta pushing this block just by gravity down this way, okay? So understand this. And this is the hardest part about physics. And it's really important that you guys get the free body diagram stuff at this level, especially for physics honors. So draw. The tip here is to draw, and then we of course can use our good old F equals ma formula that everyone loves, right? So there you have it, guys. Review these two free body diagrams. These are the most important ones in my experience, and definitely study how we derive this. So there you guys have it, guys. That's it for this video. Hope you guys enjoyed it. Please leave a like and comment for any questions that you have about the free body diagram. I am happy to answer. See you guys later.